talk session, and let's welcome our first oral talk speaker from University of Glasgow, Han Dai. Yeah.
Hello everyone. Today I will cover the topic of the multimodal BMVA fusion for autonomous driving, especially on the perception side. So let's first look at the perception sensors assembled in the autonomous vehicles, like the cameras, so that are used to capture the view information such as the lane markings, traffic signs, and other objects on the road, and also the radar sensor, which use the radio wave to detect the distance, speed, and direction of the objects around the vehicle, and also the LiDAR sensor, which use the laser beams to create a 3D map of the vehicle's surroundings, providing the precise measurements of the distance and object shapes. So it will capture the multi-view images and also the point clouds, which from the radar sensor, also the LiDAR sensor. And this is a sensor data example of the point cloud overlaid on the multi-view images. And the color shows the semantic labels of the points for the pedestrian, cyclist, car, truck, road, and etc. So with this kind of multi-sensor data, we can do 3D object detections to detect and localize the objects in 3D space around the self-driving vehicles. And we can also conduct the 3D semantic segmentation to classify each point in a point cloud into the semantic category, such as ground, buildings, vegetation, or vehicles. Another thing we can do with this multimodal data is the occupancy prediction. And this takes, a 2D or 3D input and producing a 3D occupancy grid that will represent the presence or absence of an object at each point in the 3D space. So for the input 3D points from the point cloud, they very straightforward to have this kind of BEV representation. So the input points are subdivided into 3D voxels in the voxelization process, and the voxel volume is fed to a voxel backbone and to extract the voxel features. And then these voxel features will flatten to the BEVs at the point-based BEV feature map for the point cloud. And for the image modality, and we can use an image backbone to extract the image feature, and also a depth distribution estimator here to extract the distribution for the image. When we use this image feature and this depth distribution to construct a Frosten grid here, and this Frosten grid here can be converted to a cuboid volume in the point cloud coordinate route interpolation using the camera parameters. Then we can obtain this kind of image-based voxel feature, which is similar to the voxel feature from the point cloud. And then the final stage is the same. We can flatten these kind of voxel features onto the bird-eye view, and then we can have these kind of BEV features for the image modality. So this kind of BEV representation, as we can see for the BEV features from the multi-view image, each color will represent the field of view of each cameras assembled in the car, and also for the BEV features from the point clouds. This kind of BEV feature representation preserves the image semantic density, and also for the point clouds geometric structures. This kind of BEV fusions we can unify the camera and also the point cloud features in a shared BEV space, instead of mapping one modality to the other. And for this kind of BEV representation, you may wonder why we need to have this kind of BEV representation. So the BEV representation is particularly advantageous for auto driving due to its ability to provide a comprehensive top-down view of the vehicle's surroundings. Here are some advantages. For example, for the 300-degree awareness, it will provide a complete view around the vehicle, including the object, pedestrians, and obstacles in all directions. And also, this kind of thing, this kind of BEV representation will help the algorithm to identify the object's shapes and aiding in the precise localization with the top-down perspective. And the BEV is also robust against the occlusions, even when the object is partially hidden from the side or rear views. They are visible from the top-down perspective. Another advantage of that is the BEV representation are consistent across different environments. So model trained on the BEV from one location can generalize well to the other or in a new environment. The last thing we can talk about on the BEV representation is the efficient data structure. The BEV representation are very efficient for storing and processing the large amount of sensor data. And this kind of fixed grid structure will reduce the memory requirement compared to the volumetric representations. So far, we have this kind of background knowledge. Then let's look at the multi-sensor BEV fusion framework. First, we will have this kind, on the input stage, we have this kind of input multi-sensor data. And also, with the framework we introduced, we can convert this multimodality to the BEV features we can have. So we have different resources for the BEV feature generation. And also, after we have this kind of different resource of BEV feature, we can do the BEV fusion to gather and force the BEV features from multi resources. And finally, we can feed this forced BEV feature to the task-specific heads to perform the different 3D perception tasks. So let's first look at the input stage, see what we can do in the input stage with the multi-sensor data. So what we can do something like the multi-sensor data augmentation by applying the asymmetric transformation on the point clouds, and also on the multi-view images individually. This asymmetry lies in not only the point cloud and also the camera coordinate system, but also the local cameras. Thus, we significantly diversify the multimodal data augmentation for the 3D semantic segmentation using the introduced the camera transformation and also with the preserved point cloud transformation to synchronize the different modality data augmentation. And there are also two underexploited imbalances on the radio axis in the point clouds coordinate system. So first, is the points are unevenly concentrated on the near side, because of the mechanism of the laser, the lidar sensor capturing the point cloud data. And also the distribution of the foreground object instances is skewed to the near side. This kind of imbalances leads to the training of the model to favor the semantics at the near side with a majority of the points and also the object instances. So to tackle this kind of problem, we propose the radio mix to alleviate the skewed distribution of the foreground object instances on the radio axis, and the radio mix will first augment the point clouds by selectively copying the objects from the point cloud and with the dense points and specify the virtual relevance and paste and then on the far side of the point cloud in the video translation. Thereby, will introduce plausible new distant foreground objects in the new, augmented point cloud data. And another thing we can do in the inference stage, that is, in the training stage. In the inference stage, we can do something like the TTA. The diversity and the flexibility in the input point cloud variance will help reduce the uncertainty we see in Adambo's predictions with multiple input variants. This is what we can do at the inference stage to boost the performance of the multimodal. The experimental results shows that when we combine the 4 individual TTA transformations, is slightly better than reusing the individual transformations multiple times. And the last 3 rows in this table shows that the performance can be further improved with the increased capacity of the point cloud input, but this kind of improvement gradually structured, because of the limitation of the TTA techniques. And for another part we can do in the feature level, because we have multiple resources of the features, and then we can do the knowledge distillation in the BV features from multiple resources. The general idea is very simple and straightforward. We can use a LiDAR-based 3D detector to serve as a teacher model for providing the feature-level training guidance. And this can distill more accurate 3D measurements from the point modality to the image modality, for this kind of knowledge distillation techniques. To enhance the BV feature representation capability, and we can use a BV fusion module to unify the multimodal features in a shared BV representation for task agnostic learning. So to achieve that, we can use a 3D reference point to serve as the anchor and gather the information from these BV features from the 3 modalities. And this initial reference point does not depend on the features from any sensors. It will update it dynamically after parsing the features from all modalities. After sampling this kind of BV features from all the modalities, and we can parse the features and update the queries using the self-attention module and the FFM layers in the transformer decoder. And also this kind of transformer decoder can be scalable to a large models. Because of the transformer layer, we can make it deeper and deeper, depending on the capability, capacity of the hardware. So with this kind of multi-sensor BV perception framework we have seen here, we can investigate some very interesting things, like what really matters for the multiple sensor BV perception. Some important factors, for example, just the input resolution for the multi-view images. The early BV method downsample the RGB image input before feeding it to the model. But the latest models we have here can use higher and higher input resolution. But we find that not always higher resolution, the better performance. There is you can see that there is a drop in there. And also for the bench size, we can use to train such a model. It's a large bench size will give us a better performance, because the large bench size may provide a smoother or more accurate estimate of the gradient, which might help in escaping the sharp minimum or reaching better generalization capability. And also we see that when increasing the size of the model, of the backbone, and we can see the model can achieve better performance. And finally, for the different modalities, when we combine them, the camera plus the radar model is better than the camera-based model. And for the camera plus LiDAR model is better than the camera plus radar model. And also, when we combine these three modalities together, it will slightly better than the camera plus LiDAR model. So what we can have here today is that we, for this kind of BEV fusion framework, it can unify the multimodal features in a shared BEV representation, and also the techniques in the input stage. We see that, like the asymmetric multimodal data computation, radio mix, also the TDA, can improve the performance of the multi-sensor BEV perception. And also other important factors for example, in the image to BEV generation. There's some important factors like the input resolution, bench size, and backbone, and so on and so forth, will influence the performance of this kind of image to BEV feature generation and the BEV feature representation capability. And the last thing we have here is that the multi-sensor fusion is essential for an accurate and reliable autonomous driving system. That's all for today's talk, and you can scan these the QR codes to find the related project on the GitHub shared GitHub page. Okay.
We have time for one question. Any question?
I have a question here. So, when you're talking about apply multimodal models in self-driving system, do you see any real risks? I mean, safety problems.
Safety problem.
Yeah.
You mean just on the perception side, or?
Yeah, on the perception side, from high level, like when you're talking about like query-based attacks or potential to backdoor the video perceptions, like is there any similar risks you thinking about?
So for example, in the occupancy prediction, this kind of perception task, for the top-down view, there's something maybe hidden from the some objects. Maybe they are just under that object. For example, the tree or the vegetation in the street. We can't locate the presence or the absence of some objects when they come across these kind of obstacles. So it will use maybe some temporal information to tackle this kind of challenge and to help us have a more sufficient information to the autonomous vehicle and make the decisions. Yeah.
Thank you.
Thanks, Dr. Hang Dai. Let's come to the second talk.